Hello, Sai 10. I hope everyone's having a great weekend. I heard some of you were having a little bit difficulties as we transitioned online, so I'm making this video kind of summarizing what we did this week. Okay, so on Monday we started out by talking about uniform motion. So uniform motion occurs when we're traveling at a constant speed. In real life, this is almost impossible to achieve because we have friction and air resistance that's impacting our speed as we move. However, for now, just recognize that, for example, walking is a very close representation of uniform motion. Next, we looked at scalar versus vectors. So scalar will be your time, your mass, your distance, and your speed. Vectors will be like your displacement and velocity. Vectors have a sign on the top to indicating that it's a displacement versus scalars, right? There's no hat at the top. Vectors also have a direction. Scalars don't. Next, we talked about distance. So distance is a scalar quantity. So that means if I travel 4 meters east and 6 meters west, then my distance will be 10 meters. Displacement wise, for the same example, we would have been minus 2 meters or 2 meters west. Here's kind of an overview picture, so you can just think of displacement as kind of your overall movement, and your distance as your individual steps. These are the positive direction when it comes to our vectors, so your forward, up, right, east, and north. And these are your negative direction, so your backwards, down, left, south, and west. Next, we calculated some displacement here, right? So for example, this one about John, his displacement is going to be 1.9 kilometers north, and that's because he went south and then he went north. If you added these two things together, the minus 4.3 and the 6.2, you should have gotten 1.9 kilometers north. We also looked at what would happen if he traveled both vertically and horizontally. So here he traveled 11 kilometers north and 11 kilometers east. So what that means is it looks like this triangle here. And the key thing is that we're trying to look for this part here. To solve for c and not c squared, we need to square root this as learned in grade 9 math. So to solve this, we need to use Pythagoras theorem and go a squared plus b squared and take the square root of that. So if you did that, then you should have gotten approximately 15.6. And next year, you will learn how to combine these vectors. But for now, you can just answer as 15.6 meters. After that, we looked at some unit conversions. So here, right, to go from kilometers to meters, you're multiplying this by 1,000. To go from hours to seconds, you're going to multiply this by 3,600. Right, so that's how they got to this number. And to go from seconds to hours, you're going to divide by 3,600. Next, we looked at how to convert meters per second to kilometers per hour. So when it comes to this, right, what you want to do here is put down your two equivalency factors. So your first equivalency factor is your time, and 1 hour is equal to 3,600 seconds. So how I got that was that there were 60 minutes, and each minute had 60 seconds. So if you did those two math together, then you would have gotten that as your answer. Okay, so so next we gotta put our length equivalency, right? So 1 kilometer is equal to 1,000 meters, and the reason why we do it like this is so that our units match up correctly, right? So we're trying to reach kilometers per hour. So that means that your meters cancel out and your seconds cancel out, and you're left with kilometers per hour. So that's how you know you did it correctly. After that, we take a look at going the other way. So from kilometers per hour to meters per second. So what you gotta do is that you gotta do the opposite way. So now you gotta multiply it by 1,000, divide by 3,600. So if you do that, the kilometers cancel out and your hours cancel out, and you're left with 27.8 meters per second. And usually when you're going from meters per second to kilometers per hour, your number is going to go up. And that's because you're doing this over an hour. So you can do a lot more in an hour. And on the flip side, if you go from hours to seconds, your number is going to go down because you can't do a lot in a second. Next, we took a look at speed and velocity. So before we did that, we took a look at time intervals. So time intervals is just defined as the final time minus the initial time. After that, we took a look at speed. So speed is distance all over the time interval. Velocity is displacement all over time. So displacement, as a reminder, you need directions for it. Velocity can be taken a look at in two different ways, right? So this is the simple way. So you use this whenever you're just given two numbers, right? Whenever you're just given one displacement number and one time number, and then you use this a simple way. If you're given us two sets of numbers, then you use it. You would use this the expanded way. So this first example here is the simple way, right? So notice here that we're only given one distance and given one time. So we're gonna just divide the 20 by the 1.5, and you would have gotten 13.3 meters per second. The second example, it's also another simple example, right? So we're given two numbers. So we're just going to divide both two numbers and get to our answer. These third and fourth one are very similar again. So these are, again, similar situations. However, the third question here is a little bit tricky here. It's asking for the time, right? How long means the time. So what you got to do here is that you got to set your equation up where it's v is equal to d over t. And you're going to multiply both sides by t, so you bring it up to the top. And then you got to divide by v, so then your v's cancel out. So ultimately, to get to t, you need to divide your distance by the speed. This example here has us dealing with negative direction, right? Because it's going south. So we gotta take this 465 and make it negative. We're gonna divide this by 0.833 hours, and that's because 50 minutes. If you convert this to an hour, is approximately equal to 0.833. Right? 5 over 6 is approximately 0.83333. So your answer here should have been negative 558 kilometers per hour. And it's also asking for meters per second. So we gotta do, the way we do that is that we multiply by 1,000 and divide by 3,600. And once we do that, then our meters per second value is negative 155 meters per second. And you can also write this as 155 meters per second south. This one at the bottom here is asking for displacement. So displacement, you're going to calculate that by multiplying your velocity times time. Right? And that's because here you multiply t on both sides, then you isolate for d. And all in all, if you did this math correctly, then you should have gotten 1.08 times 10 to the power of 4. Initially, you would have gotten this, 10,800, but because we're working with 3 significant digits, you got to convert this into 3 significant digits. So the way we do that is through scientific notation. And that's because there's nothing you can do rounding wise to get this number to 3 significant digits, right? You can't like shrink 10,800 further. So what you gotta do here is gotta take your first 3 numbers and you look at your 4th digit. If it's 4 or less, you keep it the same, and if it's 5 or more, you round up. Since it's 0, we keep it the same. So the 3 digits that we're gonna take is 1.08. Now that we established our first number, we'll look at our second number here. So how I got to the 10 to the power 4 was that I started at the leftmost digit and I went to the rightmost spot. So that's 1, 2, 3, 4. So it took us 4 steps, so that's why it becomes 10 to the power of 4. Some of you on the quiz, answered it as like 1.08 times 10 to the power 6 or 1.08 times 10 to the power 2. That's incorrect, and that's because when we convert to scientific notation, this number and this number needs to be approximately the same, right? So we're not, when we go to scientific notation, this number is not going to be any different. Also, some of you answered it with other number, with like something like this, 10.8 times 10 to the power 3. Unfortunately, that's also not correct, and that's because this first number here has to be between 1 to 9.999, okay? Whoever invented scientific notation a long time ago decided that that's the proper format, and that's the one we follow through. This example here is one we have to use a more complicated example. And that's because we're giving two sets of conditions. The sprinter started out at the 100-meter mark after 11 seconds. And he ended at the 200-meter mark at 23.1 seconds. So to get to our speed, this is our final condition, the 200 meters and 23.1. This is our initial condition, the 100 meters and the 11.0 seconds. And if we've done this math, you should have gotten 8.26 meters per second as your answer. Next, we took a look at acceleration. So this is defined as the change in velocity over the change in time. And it's important here to know that this is a vector, so that's why there's a sign above. Positive acceleration happens when you're both traveling in the positive direction and speeding up. So in other words, your final velocity is higher than your initial velocity. It can also be achieved when you're going negative direction and slowing down. So in other words, if you're going south and your initial velocity is higher than your final velocity. We have negative acceleration, so that's when you're traveling in a positive direction and slowing down, or if you're traveling in a negative direction and speeding up. So we had a couple examples. So the first one asks us to calculate the acceleration of a car. Our final speed, our final velocity is 15.2, and our final velocity is 4.5. And our time interval is 25 seconds, right? To determine the acceleration, you would have to done 15.2 minus 4.5 divided by 25 seconds. And our answer should have been 0.43 meters per second squared. Our next example about the bike riding. So this is where this example comes into play. Negative direction and slowing down, right? Because we're going west and we're slowing down. So to calculate acceleration, right, our final velocity is 3 meters per second and our initial velocity is 15 meters per second. So what we gotta do here is gotta do 3 minus 15, and you get a minus 6 meters per second west. Apologize, a little hard to see, but that is minus 6. My eraser wasn't working, so this is minus 6. Let me just fix that for you in a second here. Minus 6 meters per second west. Because we have a minus sign, and west, we can cancel those both out, and our answer, leave the two negatives cancel each other out. We can leave our answer at 6 meters per second squared. This question, it wasn't the best because it didn't have a direction, but on a test, I promise you that I'll have a direction so that you aren't confused. Because normally with acceleration, you need a direction, but obviously, whoever wrote this question omitted the direction. Alright, so this is what we did on Friday. So this is what the graphing skills. So your manipulative variable is always going to be the one on the bottom, and your responding variable is always going to be vertically here. So the manipulative variable is a variable that you have control over, or one that you change. Responding variable is the results you're going to get. And looking here, this is where your manipulative variable is going to be, and it's pretty much always going to be in really nice and round numbers. So like your 10s, your 5s, your 15s, and so forth. This here will be like the not so nice number, because that's what you get from your like your scientific instruments. And These numbers here are kind of calculated by the instruments, and they don't always look pretty or nice. They don't always be like 10, 15, 20, and so forth. So we ended off our week on page 20. So page 20 talks about what we need to do when it comes to graphing, right? So we need a title. So this needs to be y versus x. So our y variable is here, our x variable is here. And make sure that you have your units and your axis labeling. Once again, you get a label and make sure you have your your units. To determine slope, we're gonna pick 2 points on the graph here. So if you look down here, I picked the 30 and 70 and 0 and 0. So my final condition is 70 and 30, and my initial condition is 0 and 0. If you did this math, you should have gotten 2.3 meters per second. And that's how you determine slope. And oh yes, we also talked about 3 conditions of slope. So this is the one you see most often here, this one here. That's when something's moving. So this line here is when we have a positive slope. This one here is when we have negative slope. Alright, and that's because when you do the slope calculation, you're going to get a negative number. And when you do the slope calculation, you're going to get a positive number. This one here is when if this was a distance versus time graph, so if this was this, then this is when you stop moving, right? Because you're at this distance constantly over the entire time, right? So you're not gaining any distance. This one here is when you're moving infinitely. This is theoretically impossible to achieve in real life because in our universe we always have resistance slowing us down, so we can't infinitely achieve distance. Eventually we have to slow down. But however, for the science 10 sake, we want to show this to you, and that whenever you have a vertical line, that's when your slope is infinite slope. And in math, we represent this with the infinite sign. We also we learn about the line of best fit. So line of best fit is also just talks about how you're going to draw a line through where most of your data points are, right? So most of my data points are here, so I'm going to draw a line like this. Most of my data points like this, so we're going to draw a line like that. Okay, yeah, so we actually ended off here. So, when it comes to the distance versus time graph, is most often used to analyze the motion of whatever the object's moving. So the slope of this is the average speed. The way we calculate slope, once again, is to find 2 points. So for this example, I picked this point and I picked that point. So this point is here and this point is here. To calculate slope, right, is rise over run. So this is 20 minus 0, 4 minus 0. So your slope should have been approximately 5 meters per second. If you get somewhere along the lines of like 4.8, 5.2, that's okay too. As long as you're in this ballpark, then we'll be fine, right? Because some of us take different data points. Alright, so we ended off this week by talking about the different, comparing some of the trends we see in distance versus time graph, right? So if it's horizontal, that means it's not moving. And the steeper the slope, so the more like this, the faster it moves, right? So, for example, an airplane might have moving like this on a distance time graph. And, for example, when you're biking, it might have been moved like that, right? So, this is really fast. This is really slow. That basically wraps up our week. And we'll see you on Monday. Have a nice weekend.